Hello, welcome to my final year project presentation. I am Ain Karina binti Multaman with metric number S56118 from Bachelor of Science Chemical Sciences from Faculty of Science and Marine Environment, University Malaysia Terengganu. My project title is Highly Fused Aromatic Chalcone as Potential Organic Light Emitting Diode, supervised by Professor Tawan Muhammad Khairul bin Wan Muhammad Zain. Today, here's the talk's outline.
I will begin by introducing my project. Basically, OLED is multi-layer structure that consists of molecular electronic as single molecule. In my project, I use chalcone derivative as it contains the conjugated system and the delocalization of compounds by electron that exhibit electrical characteristics so that this derivative can serve as molecular device owing to the unique electron transport structure. Secondly, in view of the problem statement in this study, there are some issues which is stated in the pie chart above, which is chalcone derivative are having flaws, still relatively new and have the potential to be bright, but in this study, there is some solution to overcome the problems. Next, this is aim of the study. In this study, according to Weja et al. 2019, thin layer of organic material sandwiched by two electrodes is a common fundamental construction of an OLED. As in order to attain high performance and discovery of their potential, an efficient OLED must have a multi-layer structure that contains IT or anode, hole transporting layer, an emitting layer, an electron transporting layer, and also metal cathode. As stated in introduction, conjugated fused aromatic chalcone system where the push and pull effect is represented in the donor pi acceptor system, allowing electron movement and increasing of charge transfer. Mobility also support the fact that some chalcone derivative with suitable electron push-pull pair are known to be luminous. Here also some previous study for chalcone derivative with luminous properties. The methodology that were utilized to attain the purpose in this study is first, the theoretical assessment via Gaussian 09W and experimental. The computational study was carried out by using density functional theory B3LYP 631G-DP basis set will be implemented in the Gaussian 09 program package. Here is synthesis pathway of proposed compound via Kleisen-Smith condensation, which is all proposed compound AA, AB, and AC were successfully synthesized. The evaluation of OLED's potential on this study including thin film fabrication, conductivity measurement, and electroluminescence testing. For the result, theoretical results that were already being analyzed first, optimized molecular geometry that show the bond length, bond angle, and torsion angle. Next is energy band gap as shown in the slide, which is AC exhibit the lowest value and the energy band value of all compounds shows their potentiality as semiconducting materials. And last, for the theoretical result is molecular electronic potential, MEP result that show the electrostatic potential of chalcone derivative in sequence AC, AA, and AB. For experimental result, the synthesis progress of all compounds was successfully synthesized. The AA product obtained is 43% as yellow needle-like crystalline solid, AB product obtained is 82% as yellow crystalline solid, and the AC product obtained is up to 55% as crystalline solid. Next, for the characterization, first is FTIR of AB as representative where several peaks can be seen in comparison spectrum of theoretical and experimental, which is the aromatic CH stretching frequency appear in the range of 3100 until 3000 cm1 at theoretical spectra, while the experimental observed vibration in the range 3050 until 3040 cm1. C double bond O bands for this compound occur in that range, which might be mostly due to a result from the resonance effect of carbonyl group with the pennyl ring and intermolecular hydrogen bonding in the molecule. The bands between 1500 cm1 and 1650 cm1 in chalcone derivative are usually assigned to C double bond C stretching modes for the theoretical and experimental result as it conjugated with C double bond O. OH NMR is revealed aromatic CH in the spectrum of AB as representative in that range due to resonance characteristics that are strongly influenced by the para-substituted position of epoxy group at the aromatic ring, while C double bond C revealed at delta H 7.38 ppm and delta H at 0.62 ppm. The epoxy group at the aromatic ring can be seen at around delta H 1.45 ppm for CH3 and delta H 4.11 ppm for OCH2 as it detected downfield and were shielded due to their close proximity to the electron withdrawing oxygen atom. Carbon NMR spectra of C double bond O occur as single resonance due to the shielding effect because of the presence of oxygen atom. Observation of two resonance C double bond C were due to unsymmetrical structure of the compound. the chemical shift of CH3 occur at delta C 14.73 ppm, while CH2 allocated at delta C 63.68 ppm as it more deshielded than CH3. UVB spectrum absorption band in the range 242 to 243 nanometer can be assigned to pi-to-pi star transition of the aromatic system. C double bond of broadband were believed to exhibit pi-to-pi star transition at about 267 to 275 nanometer and N-to-pi star transition. The epoxy group of absorption band can be seen at about 290 to 325 nanometer, assigned to N to pi star transition. And lastly, C11C broadband exhibit N to pi star transition in that range. For UV fluorescent, the intensity of excitation and emission with high stock shift shown that AB suitable to be used as emissive material in OLED. However, in this study, AA and SC not fluorescent due to steric hydrants from the molecular framework which reduce quantum yield. That could be owing to substituent connected to chalcone derivative. For CH elemental, AA show tiny difference but AB reveal considerable differences attributable due to minor levels of contaminant or the sample moisture content. Next, for the thermal stability of AB, total weight loss is 67.4% from first to second degradation. As representative, AB shows the oxidation is quasi-reversible as can be observed at figure below with redox potential for FeL within a Rayleigh-limited range 0.46 volt. And lastly, for the result is OLED testing and the conductivity measurement was conducted. Thus, as the result, AA, AB and AC can be employed in rectification application such as OLED. Here is shown the fabricated thin films of AB as representative depicted the emitting light that show their functionality as OLED material. Finally, the conclusion for this project is AA, AB and AC were fully synthesized. The energy gap study showed that the value is still in the range that shows their potentiality as semiconducting materials. Besides, in this study, can be concluded that the presence of pi-conjugated system enable the delocalization of electron, result in show the ability of the compound conducting the electrical current. Also, as AA, AB and AC shows purple light emitted, it displays their electroluminescent behavior. For the recommendation, the further research and additional work can be carried out, for example, in the selection of more bulky compounds and elongation of substituent chain, addition of characterization instrument to more accurately identify energy band gap. Also, combine further research of another optoelectronic application. Because of these promising discoveries, it has opened up enormous and broad opportunity for further study in various sectors, which may lead to relevant application. Last but not least, the gratitude to all that are involved in this study. I sincerely appreciate your attention this morning. So, to finish my presentation, I did like to say thank you, stay safe and stay healthy.